In the last several videos, we've been analyzing differential equations that are second order, linear, and homogeneous. And to give you a quick example of that, I'll just give you this one. So y double prime minus 2y prime plus y equals 0. The 0 over here means that it's homogeneous, right? When it's equal to 0, that's homogeneous. The fact that we've only got y double prime, y prime, and y rather than sine of y or some other function of y indicates that this is a linear differential equation. And then second order just means that we've got y double prime. So that's the second derivative of y. And again, the other variable here, it could be dy dx that we're dealing with. Like the y prime could be representing dy dx, dy dt, or dy d anything. Right? We don't know that yet, but that will depend on the question that we're given. So far, when we try to solve these, we realize that we can set up a characteristic equation. And the characteristic equation essentially takes these coefficients. This will be a 1, this will be a negative 2, this will be a 1, and you plop them into a characteristic equation. So that will just become r squared minus 2r plus 1 equals 0. And so far we've seen two cases, right? Whenever this is basically just a quadratic, and there are always three cases for a quadratic in terms of the types of forms that its solutions take on. You can have two real and distinct solutions, and an example of that would be r squared minus 6r plus 8. And if we were to solve this, we could write this as r minus 2 times r minus 4 equals 0. So r would equal 2 or 4. There you have it. We've got two solutions. They're both real and they're distinct. An alternative to this is, let's just change the numbers here slightly. Right? Basically, when you've got the discriminant that's less than 0, you're going to have two. Again, they're going to be distinct, so two distinct solutions, but they're not going to be real, they're going to be complex. And if we were to do that over here, we could have something like, I guess, plus 10. So we could just change this ever so slightly. So we're just changing the 8 to a 10, that's all we're doing. And now, if you try this, well, we can use an alternative approach to this. We can write this as r squared minus 6r plus 9 plus 1 equals 0, right? So that's r minus 3 whole square, that's the first three terms, is equal to, we can subtract 1 from both sides and we get negative 1. So r minus 3 equals plus minus the square root of negative 1, and of course the square root of negative 1 is nothing but I, so that's plus minus I. So r here would equal 3 plus minus I. 3 plus I is one solution, 3 minus I is one solution. So yet again, as expected, we've got two solutions, they're both distinct, but over here they're both complex. And we saw how to use these roots to the characteristic equation, plug them in back over here, and then find actual solutions, both given and not given initial conditions. Let's take a look at this other case now, because as you might imagine, there are three cases. The only other case is when you've got two solutions that are the same, right? And the two solutions that are the same will take on a form something like this, right? So this is just basically, this is the characteristic equation. And this characteristic equation right here is, of course, from this differential equation. So as you can imagine, that's what we're going to be solving in this video. And if you solve this, well, you just see this is r minus 1 whole square equals 0. So r is equal to 1. There are no other solutions for this. I doesn't work, nothing else at all. It's just r equals 1. And so based on what we know so far, we know that one solution will just be e to the rt, over here r is 1, so that will be e to the t, and you can give it any coefficient, so c, some random arbitrary coefficient c times e to the t is one solution. But we know that there have to be two solutions, right? And it's a bit difficult, like what could our second solution be? We can try e to the 2t, but that's random, like there's no reason that should work, and if you try it out, it's not going to work. That would work if r over here were 2. So there is a method to go about solving this, and it makes an assumption that, actually it's not much of an assumption. Instead of writing this as c1 e to the t, you can just change it to v1 e to the t, right? You're basically changing this, the constant, to just a more general function. So it doesn't have to be a constant anymore, it can still be a constant, but it can just be a general function. And so we're going to let our, so this is our first solution, right? This is solution 1. We're going to let our second solution, we're going to let this be v1 e to the t. Okay, so we're going to go ahead and plug this in, and when we do that, we're going to get the following. So I'm going to, if you just want to go over this a bit more, pause the video, look over it again, maybe write it down in your notes if you're doing something like that. But we're going to basically use this solution. We're going to plug it in here and see what we get. So v1 e to the t, where v1 is just some arbitrary function. I could have written v1 of t to make it a bit clearer. I just didn't for the sake of having to write less. So that's my laziness, I guess. But okay, so our second solution, y is going to be v1 times e to the t. Y prime is then going to be v1 is, remember v1 is a function, so it's not a constant. So we have to do v1 prime e of t plus v1 e of t. Okay, this is just using the product rule. Y double prime will then be, well, okay, this is going to be v1 double prime of e to the t plus v1 e to the t, v1 prime e to the t. That's from taking the derivative of that. When we take the derivative of, let me step up a little. When we take the derivative of this, we get the same thing as this yet again. So that's going to give us another v1 prime e to the t, and then one final v1 e to the t. Okay, so that's about it. I'm going to step back down. It's a bit awkward the way I'm standing right now. We've got this over here. These two terms can be simplified, so we just rewrite this as v1 e to the t, v1 double prime e to the t plus 2 v1 prime e to the t plus v1 e to the t, and this is again all y double prime. Okay, does it look a bit messy? Yes, but you'll see that it'll all simplify nicely. Why don't you pause the video, plug each of these back into this, and see what you can discover for that. Okay, so pause the video now, take a few moments, try it out yourself, and I'll show you what I do, and you can check if you got it right. Okay, so I'm assuming you've paused the video or given it a go. I'm going to work under over here where there's a bit more space. So just plugging this in, it's quite simple. v1 double prime e to the t plus 2 v1 prime e to the t plus v1 e to the t minus 2 times, well, just v1 prime e to the t plus v1 e to the t plus v1 e to the t. Is it messy? Yeah, a little bit, but again, you'll see it will simplify nicely. First of all, the v1 e to the t, v1, and remember, all of this is equal to 0. Right? That's just what we're working with. This is a homogeneous differential equation. You can, I'm not going to write it all out again, but you can see 2 v1 prime e to the t minus 2 v1 prime e to the t. v1 e to the t, v1 e to the t, multiply, add these together, you get 2 v1 e to the t, and again you're subtracting 2 v1 e to the t. So this cancels with this and this add up and cancel with this times this. So everything is left, everything is gone. Now we're left with just this, v1 double prime e to the t equals 0. Can e to the t ever equal 0? No, right? E to the t, no matter what you take, it can never equal 0. As t goes to negative infinity, it will approach 0, but it's still never going to equal 0. So because of that, we can actually just take this out. We can divide by that. And now we're left with something that looks very neat. v1 double prime equals 0. Let's integrate this once, right? So we're going to go ahead and integrate both sides. dt, I'm not going to write it, but you know what I mean, right? We're integrating with respect to t. There's no space over there. Once we do this, what do we get? We get v1 prime, right? When you're a second derivative, when you get integrated, you go down to being a first derivative. So v1 prime is equal to, what's the integral of 0 dt? It's just a constant, right? So we're just going to go ahead and call this constant c. We're going to try it again. We're going to integrate this, and we'll get v1 is equal to ct plus c1, some other constant. This is quite messy, right? And remember that our solution to this is not, v1, it's v1 e to the t, right? We've gotten v1 over here, so we can now just plug that back in here, right? And this will give us ct plus c1 e to the t. But remember, our first solution was already c1 e to the t, right? C1 e to the t. Actually, I should be a bit clear. This is not the same c1 as that, of course, right? So I'll just make this 3, make this 2, so that you can see all these constants are different. They're all arbitrary. None of them are the same or anything. None of them are necessarily the same. And when we write this, we can see the C3 e to the t, C1 e to the t, they're essentially the same thing. They're just different constants that are multiplying them. So we can ignore that for now. We can kind of just like cross that out. What else do we see here? Well, we see the main thing over here to take away is that we have C t e to the t, C or whatever, C1, C2, I think I wrote C2 over there, C2t e to the t. And this becomes our main takeaway from here, right? Because when we've done all of this, the C, like the constant C e to the t doesn't matter. That's the exact same thing as this. For all our purposes, it's the same as that. Actually, even over here, the C2, the constant in front, doesn't matter. The main solution that we've come up with over here is t e to the t, right? And that becomes our second solution. We have two solutions as we desire. We've got y1. I want to just say it. There's not too much space here. I don't want to clear it in case you're still looking at it. So I'm just going to say the solution. Our first solution is just c1 e to the t. Our second solution was initially c2t plus c3 times e to the t. But the constant times e to the t can just go back into the first solution. So we can ignore that. And we're left with c2 t e to the t. Right? So it's the exact same thing, but we're just adding an extra factor of t. And when we do this, what becomes interesting is that, again, I think I was saying this and I got sidetracked, but this C2 doesn't matter, right? It's basically just a linear combination. For any differential equation, we're going to have our solutions be C1y1 plus C2y2. So the C2 over here, the C2, the C1, those don't matter. We can take them out. The fundamental solutions that we have are just y1 and y2. And over here, that becomes e to the t plus t e to the t. I encourage you to try this exercise for other stuff, like for more, actually no, try it for the general case, right? Just write a y double prime minus, plus b y prime plus c y equals 0. Try to go through this entire procedure again. It'll be a bit messier, there'll be more variables to deal with, of course, it'll be a bit messier. But try that out and see that you do indeed get the same main idea. You should get the same thing where you get a t e to the t or t e to the negative b over 2at or whatever it may be, right? Something like that. But you should get this extra factor of t being multiplied in for your second solution. What we're going to do now is verify that this works, because a lot of this is abstract. You can, of course, plug this in and see if you get the same thing, and you will, right? That's because it's correct, right? That's why I'm sharing this in the video. But if you want to just be extra sure, one way you can do that is by using the Wronskian. If you aren't sure what the Wronskian is, I recommend you check out the video. If you're on the website, you just scroll up and you'll see it over there in the same section. If you're on my YouTube channel, just search up the Wronskian and you'll see it there. But what we're going to do, and I'll do this in a different color. We've been using black quite a bit, so let's try blue over here. The Wronskian is just the determinant. This is the determinant of y1, y2, y1 prime, y2 prime, right? We know y1 is just e to the t. So actually, you've seen the matrix, you've seen like how it's defined, so I'm just going to go ahead and plug in the answers now. So this will just be e to the t. This will be t e to the t. Remember, we took out the constants because this is just with y1, y2. The solutions that we got, c1 y1 plus c2 y2, that's a linear combination. So we don't need so we just like take out the main components of the solutions, not the constants, like the actual substantive part of that. So this is what we got. What's the derivative of e to the t? It's e to the t. What's the derivative of this? It's t plus 1 e to the t. I did that in my head because I've got more practice. If you couldn't do that in your head, just pause the video, try it out, and then see what you get, and you will get the same thing. So don't worry about that. When you do the derivative, when you take the determinant, my bad. When you take the determinant of this matrix, you'll basically get e to the t times t plus, you'll get the e to the t times this entire thing minus this entire thing will leave you with just 1 times e to the t times e to the t. So this will just, I believe, unless I've done something wrong, it should just be e to the 2t. Yeah, I think that's what you'll get. You can verify this yourself, but the main point is, no matter what value t takes on, we saw this earlier as well, no matter what value t takes on, this is never equal to 0, and thus we know that e to the t and t e to the t form a fundamental set of solutions, meaning that yes, these work, yes, they're independent of one another, and so it works exactly how we'd like it to work. I'm not going to, I think this video has taken quite a bit of time already, so I'm not going to go and give you practice questions here. The main takeaway is find your first solution using the characteristic equation, right, like e to whatever t, and then just plop in a t in front, and then the procedure when you're dealing with, when you are given initial conditions is the exact same, and you just plug them in. So now instead of t and t there, there's also a t there, so just make sure you plug in your input over there, and then you solve it the exact same way. So there's nothing really new here in terms of like the procedure to solve it. The only thing is you add a factor of t. And in future videos, when I want to deal with higher order linear homogeneous differential equations, like an example of that would be y cubed, y triple prime plus y double prime plus y prime plus y equals 0, something like this. You will see, you might end up seeing a similar formula, and over there, instead of multiplying by t times y1, you might also do t squared y1, t cubed y1, and so on. Okay, so this is not just limited to second order functions, second order linear homogeneous differential equations. It's any order essentially, right? So it's a very powerful tool, and I hope you learned something new in this video. I know it's been a long time, I've been rambling quite a bit. Hopefully you took away something useful from this video. I might or might not make practice questions on this. But what in the next few videos here in this topic, we're almost done now. We've considered like dealing with two distinct real roots, two distinct complex roots, and now repeated roots. What we're going to do next is take a look at when we have a right hand side that is not equal to 0. So non-homogeneous, right? Non-homogeneous differential equations. We're going to take a look at how you can deal with those. A lot of the stuff that you're going to need for that, don't think all of this that you did with homogeneous differential equations is useless, because you still need to know all of that to solve a non-homogeneous differential equation. There's just a little extra step that you do with that. So this is all still very useful information. You can't solve a non-homogeneous differential equation without solving a homogeneous differential equation. So just keep that in mind, and that's what you should look forward to next. If you have any questions, please comment them below, and I'll see you in the next video. Thank you so much for watching.